Okay, welcome everyone to this continuation of what is algebraic geometry. Well, today I would like to talk about one of my favorite notions in algebraic geometry, one of my favorite notions in life in general. What is dimension? Or maybe not dimension in general. So you will see in your life, in your mathematical life, you will see that there are kind of various variations of dimension. So we are in this algebraic geometry class. We are really interested in varieties. And turns out that the correct definition here of dimension is like a space in a space in a space. I have a lot of pictures to illustrate that. But just to get going, so there are really a lot of different notions of dimensions. They're kind of really fancy notions of dimensions, like fractal dimensions or something. And kind of the standard picture, what one should have in mind is, well, dimension is kind of the measure of the size of a thing. And my favorite word here really is thing. So just whatever it is, a space or a curve or an object or whatever. Just size of the measurement of size of a thingy, of like a little thingy. And what it really is depends on the problem. So vector space dimension, dimension of a surface, dimension of a topological space, something like that, dimension of a fractal space. It kind of really depends on the context. But what it should always be is it should make some intuitive sense. So if you know something like a fractal dimension, which like has a little bit of a strange definition, but if you see the examples, it kind of makes sense. If you think of just a regular dimension, which is probably just the kind of coordinates, so kind of parameters that you can change, then yeah, that intuitively makes sense. If you think about a more topological definition, let's say definition of a dimension of a manifold, then it's like covering things with smaller things, something like that. So everything kind of always makes sense, and the usual objects, the standard object, it should take the standard form, right? A surface should be two-dimensional, no matter how you define it. And yeah, the point here is for varieties, and that's kind of the whole point of algebraic geometry in general. And we kind of don't really care about we don't really want to make some definitions depending on the underlying field. We kind of want to do all fields at once, some sense. So dimension will vary a lot depending on what the notion of dimension should not vary. That's exactly the opposite of what I said before. Should not vary depending on the field, but the picture we have in mind will vary a lot. I have some illustrations as we go along. So the whole point here will be to define dimension in this algebra geometric way, which in particular means we really want to define it in some polynomial form, so some statement about rings, because eventually in algebraic geometry we're already doing it. Why am I saying eventually? We're already in the steps doing into that direction. We want to push everything to algebra, right? So also dimension should be an algebraic object. But let's start slowly. So it turns out that the correct notion of dimension in algebraic geometry is not so difficult. It's really this idea of having, well, I hope this is an okay picture. I have a point, which is like here in the middle, difficult to see, and I have a line, which is the blue one here, and I have a very obvious red plane here in the front. And it's really this idea of this nesting strategy of a point, which is like a zero-dimensional object, in a line, which is like a one-dimensional object, in a plane, which is like a two-dimensional object, in a space, which is, well, in this case, in three-dimensional space, which is a three-dimensional object, and so on, right? So, and sometimes we can say R3, which is my whole picture, so everything kind of lives in R cubed. R3 is three-dimensional since it contains a zero-dimensional space, in a one-dimensional space, in a two-dimensional space, but that's it. We can't put more inside. No, that's kind of maximal. It's kind of the supremum over everything. And why is this good? Because it's kind of makes intuitively sense. I hope it makes sense. To me, it makes sense. I have a point in a line in a plane and so on. But it also pretty much feels independent, right? You can think of a point and a line and a plane over some kind of strange field, and you can just it just makes sense somehow. And this turns out to be a really, really good notion. And the algebra version, so this will be the dimension, right? Surprise. This will be the dimension of the space, which I will write down in a second more carefully. But the algebra version is really kind of the same. but you do it in the coordinate ring. Remember that you have this coordinate ring description, and what you should have in mind is something like this. You have a chain of ideals now in your space. You have a point in a line like an x, in a plane like an xy, like in space like an xyz, which makes the letter then three-dimensional because you have a zero-dimensional thing and a one-dimensional thing and a two-dimensional thing. And people usually call that the Krull dimension, and it's really just the maximal chain, the maximal length of a chain that you can put. And kind of the correct notion, I hope I made it a little bit clear in the previous videos, the correct notion of things here should be prime ideals. So the Krull dimension is defined. It's like of the maximal length of a chain of prime ideals. A point in a line in a plane and so on and so on. And yeah, that's kind of the same as on the previous slide. What a surprise, because they are actually really the same type of object. So under the variety side, so let's say we don't have an empty is stupid. Let's say we don't have an empty variety. Then we consider a chain of closed irreducible subvarieties. Yeah, so the point in the line in the plane and so on. And the dimension is just the maximal length of all possible change. Chains, not change. Change, yeah. Chains. And a priori that could be infinite. And turns out that in all examples we ever do, it will never be infinite. So I could cross out the infinity. I just put it here because a priori I'm taking the sub over something, so my variety could be really large, but most of my varieties will live in some polynomial ring, and then everything will be fine. But anyway, hope it makes sense. We take the maximal we could put, a point in the line, in the plane, and whatever, and we have some conditions, so we don't want to do arbitrary things, and the correct conditions here would be close to irreducible. And on the ideal side, it will be just prime ideals, and you do exactly the same as I0 and I1 and blah, 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 and you take the sup over all of them, and these are the same. So the dimension of the variety is really the Krull dimension, the prime ideal one, in the coordinate ring, and this is pretty good because it's something that's a condition you can check, well, algebraic. And I now pull up a picture. So I did this illustration here. So varieties are so beautiful. Whoever came up with this idea must have been very smart. So this idea came up before people were able to do these beautiful illustrations. So here's a variety, a really beautiful one. So the green space. And it has a subvariety of a smaller dimension, which makes my variety, essentially this makes, and there is a point of course, essentially this makes my variety that you see here, the green one, two-dimensional because it contains a one-dimensional one, and the point that I haven't illustrated. So this is the vanishing set here, a nice beautiful surface. So those varieties are actually really, really nice objects. Maybe more straightforward because it's maybe not completely obvious that this thing here is actually reducible. Maybe more straightforward, here is a variety that everyone likes, I hope, defined by this equation. So the sphere, and there's a subvariety of a smaller dimension, which is, let's say, the belt, the horizon, the equator of the sphere, which is a sphere of a smaller dimension, and there's of course a point in that, which makes my sphere in the end two-dimensional. Yeah? I hope that makes some sense. And you have this picture in mind that you have a complicated variety and you pick out kind of the maximal chain of a subvariety defining its dimension. And it's really this picture of, well, there's an equator sitting in my sphere. I hope that makes some sense in some universe. And why do we want to do that? Well, because it really depends heavily on the field. So let me just do this following definition. I call space pure dimension if all irreducible components have a certain dimension. So curves one-dimensional, surfaces two-dimensional, and so on. But this really heavily depends on the field. So a complex curve, for example, is already a two-dimensional object, although it sounds like it's one-dimensional. Over finite fields, it gets even worse. So here's a curve over a finite field, and it's just a bunch of points. So kind of the intuitive definition of a dimension really breaks here over finite fields, because everything is just a point cloud. There are only finitely many things. So the curve over a finite field is just a point cloud. But the previous definition still makes sense. So you can also think about surfaces of a finite fields, which is just kind of point clouds or whatever. So the intuitive definition doesn't work, but the previous definition does work. And this is actually really excellent because you can really just in the finite world here over the finite fields, it's really easy to check that in the polynomial ring. Just a machine is very happy to take polynomial rings over finite fields and answer any question essentially you want to ask about them. But this is, I think, a really cool picture that I would like to sell here. So this is like the definition that makes intuitively sense, but we can now generalize it to some crap like this, like things over finite fields where the intuition of what dimension should be is like slightly misleading, because essentially everything is just a point cloud. I hope that makes some sense. I hope you enjoyed this video, and I also hope to see you next time.